Hello, Royals. For lesson 5.5, we are going to look at some applications of right-angle trigonometry. This should be review of the types of word problems that you've seen in grade 10 and maybe even in grade 11. We have reviewed 3 basic trig ratios, which can be remembered with the acronym either SOHCAHTOA if we're in the first quadrant, or we're just dealing with triangles. If we're looking at standard position, we might want to use SIR-KIX or TIX. I think today we'll find that we're working inside triangles that are right-angled triangles, so we'll be looking at that definition. But this only works for inside right triangles. Okay, we, of course, have seen the sine law and the cosine law used before for when we're outside of right-angled triangles. So yeah, the sine of theta being the ratio of the opposite to the hypotenuse, or the ratio of y to r, if you can write it in standard position. Cosine of theta being the ratio of the adjacent to the hypotenuse, or the ratio of x to r in standard position. And the tangent of theta being the ratio of the opposite to the adjacent, or y to x in standard position. These trig ratios do come in handy quite a bit in the real world, so we'll see some real world applications right now. When you're answering word problems, make sure you read the entire question, highlight important information, and definitely draw a sketch. Right. When you feel like you're done, reread the question, make sure that you're answering the question with units. You should be able to check and see if it's reasonable as well. And if it doesn't make sense, communicate that instead of just erasing everything. Okay, we see that a kite is 33 meters above the ground. I'm going to draw the ground. I'm going to draw a kite. Yeah. I'm going to label that height right there as being 33 meters above the ground. The kite string makes an angle of 38 degrees with the ground. That is its angle of elevation from the ground up to there would be 38 degrees. Like related acute angles, this angle of elevation is going to be measured from the horizontal. I think that comes up later. I can't think of many examples where we would measure that angle from the vertical. It says, assuming that the string is taut, which is like a weird way of writing tight, basically, means the same thing. Means the string isn't like loopy kind of thing. It is perfectly straight. How much string is let out? Oh yeah, so when you identify what it is that is being asked for, make sure that you label that as well. I'm going to call this right here L for the length of the string. And now notice in my diagram, I see a right angle triangle, an angle of focus. I'm asked to find the hypotenuse, and I'm given information about the opposite side length. So I dig up the sine ratio. I'm going to say that the sine of 38 degrees here is going to be the ratio of 33 to L. And this is one of the more awkward orientations that could happen with L being in the denominator. We have lots of practice, though, rearranging formulas. I don't want to solve for L in the denominator. I want L to be in the numerator. I'll show you 2 approaches here. One is undo a division by L by multiplying both sides by L. You might be able to do this a little bit faster with a little bit of practice. And then I don't want to undo the sine of here. I'm not taking a sine inverse. Sine of 38 degrees is going to be a number, and it's multiplying L. I want to undo a multiplication by the sine of 38 degrees by dividing by the sine of 38 degrees. Then I type into my calculator in degree mode. What is 33 divided by the sine of 38? And it didn't give me a level of precision. I'm guessing that I want maybe 1 decimal place. L is about 53.6. I'll put units in my conclusion as well. Does that seem reasonable? Well, I would need to let out more chord than the height right here. Like the least amount of chord that I could let out would be 33 meters. So this looks like, I don't know, if you ask me to guess, it looks like it could be about double. Yeah, a little less than double, I guess. Okay. The alternative to, if you have the equation, the sine of 38 degrees equals 33 over L, try writing a denominator of 1 there. You are allowed to reciprocate both sides of a proportion. You should not be using cross multiplication. And then, to undo a division by 33, I multiply the numerator of both sides by 33. Those eliminate, gets me L equals 33 divided by the sine of 38 degrees. So this was just an alternative approach. Gives me the same conclusion. There is about 53.6 meters of string. Okay. In some word problems, you might be making assumptions. These assumptions are usually pretty safe. Like, for example, if we have a wall, go ahead and assume that that wall is vertical, unless you're told that it's leaning. So we have a side view here, a vertical wall, and we have a 4-meter ladder leaning against the wall right there. We're told that the bottom of the ladder is 2.5 meters from the wall, and we're asked to figure out the angle that the ladder makes with the ground. This is one case where I could see us finding a vertically oriented angle, because maybe we would want to know the angle that the ladder makes with the wall. We don't in this question. We want the angle that the ladder makes with the ground. Once again, I see a right-angled triangle. I have an angle of focus. I'm given information about the hypotenuse and the adjacent. Sounds like a job for the cosine ratio. Not the cosine law, just the cosine ratio. Cosine of theta, I didn't talk about units in the last question. You can pretty much trust that your units are going to work out. It's going to be 2.5 meters divided by 4 meters. Meters divided by meters is unitless. I ask my calculator for the inverse cosine of 2.5 divided by 4. I don't think you need to divide 2.5 by 4 first and then write down that approximation. Let's just go inverse cosine of 2.5 divided by 4. And I forgot to estimate again. I don't know. That looks like it's bigger than 45 degrees. A little bit bigger than 45 degrees. 51 degrees. That sounds about right. Angles are 1 degree is pretty small, so we're almost always just looking for the angle to the nearest degree. Let's say the ladder is about 51 degrees off the ground. And we're done. Let's try another. A balloonist, which I'm guessing is like a pilot of a hot air balloon, records her altitude, that's a fancy word for height, as 1,208 meters. Sounds like I should probably read the whole question before I draw. With the angle of depression to her landing spot to be 17 degrees. How far is the landing spot from a point on the ground directly below the balloon's current position? Okay, I think I got it. Make sure you practice drawing your own diagram. This is sometimes where students get stuck, but you have to be able to draw your own diagram. This altitude is going to be measured vertically. Don't worry too much about your diagrams being drawn to scale. Like, you don't need a protractor, for example. So that's where the balloonist is. Hot air balloon. Oh yeah, so majestic. The angle of depression and angles of elevation are measured from the horizontal. So think of it this way. The balloonist up in the balloon needs to, if someone's depressed, they're feeling down. The person in the balloon, the comfortable position for her eye would be out along the horizon, a horizontal line. She needs to look down 17 degrees. That looks a little big, but that's all right. Down 17 degrees to see her landing spot. Let's call that L right there. Here's the balloon, B. Here is the spot directly on the ground, directly below the balloon. How about G for ground instead of B for below? What we're trying to do is figure out the horizontal distance that the balloonist needs to travel. How far is the landing spot from a point on the ground directly below the balloon? Let's call that, I don't know, D for distance. Now you might notice the 17 degrees isn't inside this triangle. We have a couple of options here. I'll illustrate. Option number one is create a triangle over here where you have an angle of 17 degrees inside. Recognize that this distance is also D. Recognize that this height is also 1,208. And then you can work in that triangle. Option number two is you label this angle, and off on the side here you show me that theta is going to be the complementary angle for 17 degrees, so 63 degrees. You label that 63 degrees and then you go. My favorite approach, though, is using our old friend, alternate interior angles. That horizontal sight line is parallel to the horizontal ground here, which means that if I come in along this horizontal, down that secant, and out this horizontal, these two alternate interior angles are going to be equal to each other. You may recognize it as the parallel line theorem, Z pattern. And it's useful because it shows us that an angle of depression for the balloonist to the landing spot is going to be equal to the angle of elevation or inclination from the landing spot to the balloon. And imagine like an ant up here on the balloon would have to look down 17 degrees to see the landing spot. An ant at the landing spot would have to look up 17 degrees to see the balloon. I like this approach best because it means I'm not moving as many numbers. I'm working inside the triangle that I'm drawing, and I don't have to calculate another value. It will show you, though, since 63 degrees is the complementary angle of 17 degrees, that looks like I'm going to be using tangent ratio. Someone might use a tangent ratio with a different orientation. I see a bit of a disadvantage of using this 17 degrees as my angle of focus. That's going to make this the opposite, and that means that the side that I'm looking for is going to be the adjacent. So I'll show both approaches. I'll show the approach that uses the 63 degrees. The disadvantage that I'm talking about here is if I write the tangent of 17 degrees as the ratio of 1,208 over D, oh no, my unknown's in the denominator. Well, that's not a big deal. I reciprocate both sides. Multiply both sides by 12,008. Do as much as I can before reaching for my calculator so that I touch my calculator once. And I ask my calculator, what is 1,208 divided by the tangent of 17 degrees? And I get about 3,951.2 meters. Angle of depression of 17 degrees isn't that steep, which means I can see on my diagram this side length should be longer than that one. I don't think I would have made the prediction that it was like triple, more than triple. But that's because my diagram's not drawn to scale either. Okay. Or if we had calculated the 63 degrees, then we could have had, and that's not a hard calculation. I'm not sure I should really avoid it. The advantage is that my unknown is going to be in my numerator instead. In this triangle right now, I would say the tangent of 63 degrees is going to be the ratio of D over 12,008. I multiply both sides by 12,008 in the numerator. Sorry, not 12,000, 1,208. And that gets me D is, ask my calculator, what is 1,208 multiplied by the tangent of 63 degrees? And, oh, did I not calculate my complement right? Yep. Wonder how long you've been screaming at the video for. Subtraction. Come on. 73 degrees, 73 degrees. Let's try that one again. 1208 multiplied by the tangent. 73. There we go. 3,951.2 meters, which sounds familiar. I don't think that should be a problem for you. Hopefully you can subtract 17 from 90, or you check with the calculator and you wouldn't make the mistake that I did. Because, yeah, the only way that I would have caught that mistake was if I had already done the question before. Either way you do it, let's conclude. How far is the landing spot? Oh, I'm just going to say it is about, I don't need to use all the words again, 3,951.2 meters away. Horizontally, right? The diagonal length here might be interesting if she's going to come in for a landing. Like, whoosh. And one last one. You can tell this is a Mr. Arnold question because it has Star Wars in it. Ewoks. The diagram on this one's maybe not as intuitive as the others. The Ewoks have set a log trap for Imperial walkers on Endor. We don't need to know what any of that is. 2 logs are suspended from the same point, both tied to 15-meter ropes, and the logs are pulled in opposite directions and tied off, ready to be released so that they crush both sides of the walker's head. This is from the Return of the Jedi, episode 6, I guess. Ewoks are like squirrels that can walk. And there's this big robot. I can't draw a walker very well. Yeah, whatever. Yeah, and the robot walks through, and the Ewoks, they cut the cords, and the logs go crush and smashes it. Okay. The ropes are 15 meters long each. They're probably vines. The logs are pulled off. If the angle between the ropes is 75 degrees, how far apart are the logs? I don't know. Let's use F for how far apart the logs are when they're first dropped. So if you're real strong with your trig from grade 10 and grade 11, you might recognize this as an opportunity to use the cosine law. And we could come back to this question and review it when you have the cosine law. If you're not given the cosine law, then we're going to have to sort of do something else ourselves here. If we draw a perpendicular, it's going to bisect this side right here. Okay, so I'm going to call this h for half the distance there and h for half the distance there. That bisector is also going to bisect the angle, so I'm going to call this theta and that there theta. This is a weird case because we are going to have to learn how to work with non-right angled triangles. We can do that later, I suppose. So here's h, half of the distance that I want. There's 15 meters. Here's theta. I'm going to show that theta is going to be 75 degrees divided by 2, which is going to be 35 and 2.5, so 37.5. Let's check that. Yeah. 37.5. So we're set up to have an opposite and a hypotenuse. Let's tell our reader that the sine of 37.5 degrees should be the ratio of h to 15. Multiply both sides by 15. And I see what I want to type into my calculator. 15 times the sine of 37.5 degrees is about 9.1 meters. This is where it's a good idea to reread the question. How far apart are the logs? Oh, that's not really what I wanted, was it? I'm just going to show my reader what I'm doing. F is going to be 2 times h, or 2 times 9.1. So they're going to be about 18.2. The logs are originally 18.2 meters, or about 18.2 meters apart. Okay. Practice drawing diagrams. And don't just look up a diagram in the answer and then work from there. Of course, it's going to be easier once you have the diagram, because really the trig is grade 10 trig. It's the drawing of the diagram that is probably going to be the challenge for some of you. So practice that and try it out.